For over 10,000 years, humanity has looked at the sky and asked one simple question: how long is a year? From the stone pillars of Göbekli Tepe to Egypt's 365-day calendar, from Sumerian lunar tracking to the precise Maya long count, from China's early solar calculations to the Andean towers of Chankilo, civilizations across the world tried to measure time. Some watched the moon, some followed the rising sun, some carved their knowledge into stone. And in 45 BCE, Julius Caesar changed everything with a reform that still shapes our lives today. This is the forgotten story of how ancient minds captured the rhythm of the earth and built the calendar we still live by. Chapter 1. Nabta Playa, Africa's stone circle of the sky. Far in the southern desert of Egypt, near the border with Sudan, there is a dry basin that once held water. Today it looks empty and silent. Wind moves across flat sand and scattered stones. But around 6,000 years ago, this place was alive. Grass covered the ground, seasonal lakes formed after summer rains, cattle grazed nearby, and in the middle of this ancient landscape, people placed stones in a careful circle that still stands today. This place is called Nabta Playa. Nabta Playa lies about 100 kilometers west of Abu Simbel, deep in what is now the Sahara Desert. But during the early Holocene period, between roughly 9,000 and 4,000 BC, the Sahara was not a desert. It was a green landscape shaped by stronger African monsoon rains. Seasonal lakes filled low basins like Nabta Playa. These lakes attracted small communities of pastoral people who herded cattle and moved with the seasons. In the 1970s, American archaeologist Fred Wendorf and his team began surveying this remote region. What they found changed how historians think about early African societies. Beneath the sand were stone tools, pottery fragments, hearths, and animal bones. Radiocarbon dating later showed that people had lived here as early as 7,000 BC, but the most surprising discovery came in the form of carefully arranged stones. At the center of the playa, archaeologists uncovered a small stone circle about 4 meters across. Several upright slabs stood in a ring. Inside the circle were additional stones placed in specific positions. At first glance, the structure looked simple, but closer study revealed something more deliberate. Radiocarbon dating of charcoal found near the stones placed the construction of the circle between 5,000 and 6,000 years ago, around 4,500 BC. That means Nabta Playa predates Stonehenge in England by at least 1,000 years. It was built long before the pyramids of Egypt. It belongs to a time before pharaohs, before writing, before large cities. The people who built Nabta Playa were not part of dynastic Egypt. They lived thousands of years before the rise of the Old Kingdom and the puzzle of pyramid power. They were cattle herders who moved across the savanna-like Sahara, yet they created one of the oldest known astronomical stone structures in the world. Researchers began to study the alignment of the stones. One pair of larger slabs seemed to frame a specific direction on the horizon. In the 1990s, astrophysicist Thomas Brophy and other researchers suggested that this alignment pointed toward the sunrise at the summer solstice. At this time of year, the sun rises at its northernmost point on the horizon. In the ancient Sahara, the summer solstice mattered deeply. It marked the beginning of the monsoon season. Seasonal rains would soon refill the lake at Nabta Playa. For pastoral communities, this meant fresh grass, water for cattle, and survival. If the stone circle marked the solstice sunrise, it could have served as an early solar calendar, helping people predict when the rains would come. The idea is powerful. A small group of herders watching the sky, noticing patterns, and placing stones to mark the sun's return to a specific point each year. It suggests careful observation over generations. It suggests memory, planning, and shared knowledge. But archaeology is cautious. Not all researchers agree on the precise astronomical meaning of the site. Some argue that while the stones do align roughly with the solstice, the margins of error are wide. The slabs are not perfectly shaped or evenly spaced. The structure is modest compared to later monuments. Wind and erosion may also have shifted stones over time. Still, even skeptics agree that Nabta Playa shows intentional design. The stones were quarried from nearby outcrops and transported to the site. Some weigh several hundred kilograms. This required coordination and effort. The builders were organized. They had reasons for choosing this exact place. Beyond the central circle, archaeologists found other features. There were stone alignments stretching outward in lines. There were tumuli, small burial mounds that contained cattle bones. In some cases, entire cows appear to have been buried in carefully prepared pits. These burials suggest ritual behavior. Cattle were central to life at Nabta Playa. Rock art across the Sahara shows that early pastoral groups valued their herds deeply. In many African cultures, cattle symbolize wealth, identity, and spiritual connection. At Nabta Playa, the burial of cattle may have had religious meaning. It suggests ceremony, not just survival. The presence of ritual cattle burials near a possible solar calendar raises new questions. Were the people of Nabta Playa combining sky observation with spiritual practice? Did they see the movement of the sun as connected to the health of their herds and the return of rain? Climate studies help explain why such knowledge would matter. Around 6000 BC, the African humid period began to weaken. Monsoon rains slowly decreased. The green Sahara started drying. Lakes shrank. Grasslands faded. For communities dependent on seasonal water, predicting rainfall became more urgent. Nabta Playa sits in a natural basin that filled only when rains were strong enough. As climate shifted, the lake may not have formed every year. Careful sky watching could offer clues about timing and change. The summer solstice became more than a day. It became a signal. Over time, the environment around Nabta Playa grew harsher. By around 3000 BC, the Sahara had largely transformed into desert. The pastoral groups who once lived there migrated east toward the Nile Valley. Some scholars believe these migrating communities may have influenced the origins of Egypt before the pharaohs. Cultural elements such as cattle symbolism, ritual practices, and knowledge of seasonal cycles may have traveled with them. This idea connects Nabta Playa to a larger story. Before Egypt became known for pyramids and kings, there were earlier cultures adapting to environmental change. The unification mystery of the first pharaoh would not unfold for another 1,000 years. But the roots of organized society, shared ritual, and timekeeping may stretch back to places like Nabta Playa. Excavations at the site reveal pottery decorated with simple patterns. The style is known as early Khartoumware. This pottery helps date occupation layers through comparison with other African sites. Radiocarbon tests on charcoal from hearths confirm repeated settlement between 7000 and 4000 BC. The stone circle itself belongs to the later phase of occupation, when social complexity appears to have increased. Researchers also discovered deep wells dug into the Playa sediments. These wells reach groundwater during dry months. Digging such wells required planning and cooperation. It suggests that these communities were not simply wandering. They returned to Nabta Playa seasonally and invested labor into the land. Some scientists proposed even more ambitious astronomical interpretations. Thomas Brophy argued that certain stone alignments may correspond to specific stars, including those in Orion's belt. However, these ideas remain controversial. Most archaeologists agree that while solstice alignment is plausible, complex star mapping is harder to prove with current evidence. The debate itself reflects how important Nabta Playa has become. It challenges older ideas that early monumental architecture began only in the Near East or Europe. It shows that complex thought and sky observation were developing in Africa during the 5th millennium BC. There are no written records from Nabta Playa. There are no inscriptions explaining its purpose. What we know comes from excavation reports, radiocarbon dates, soil analysis, and careful measurement of stone positions. This is not a mystery built on legend. It is a story built on evidence, even if that evidence leaves room for interpretation. In 2006, parts of the stone circle were relocated to the Nubian Museum in Aswan to protect them from damage. The original site remains exposed to the desert. It is not a tourist monument like the pyramids. It stands quietly, far from cities, as it has for thousands of years. When we look at Nabta Playa, we see more than stones. We see one of humanity's first attempts to measure time through the sky. The builders likely did not think in terms of astronomy as we do today. They thought in terms of rain, grass, cattle, and survival. But by marking the solstice, they were marking a year. That simple act represents a turning point. To measure a year is to understand that time repeats. It is to plan beyond a single season. It is to connect memory with expectation. In this way, Nabta Playa stands at the beginning of a long human journey toward calendars, agriculture, and eventually state societies. Long before the Middle Kingdom in Egypt's silent golden age, long before temples aligned with the rising sun along the Nile, people in the Sahara were already watching the horizon carefully. They were placing stones, not randomly, but with intention. Nabta Playa does not offer grand walls or towering blocks. It offers something quieter. It offers proof that early pastoral communities were thoughtful observers of their world. They responded to climate change not only by moving, but by organizing knowledge. Today, the Sahara is dry and vast. The monsoon no longer fills the basin as it once did. The cattle are gone, the seasonal camps have vanished, but the circle remains. In its shadow, we are reminded that civilization did not begin suddenly with kings and cities. It began with people who looked at the sky and asked when the rains would return. It began with stones placed carefully in sand. Nabta Playa is not just Africa's stone circle of the sky. It is a marker of human awareness. It shows that even in a changing and uncertain world, people sought patterns, built memory into landscape, and measured the passing of the sun. And in that quiet act of observation, the first calendar may have been born. Chapter 2. The Egyptian Civil Calendar. The first 365-day year. Long before clocks, long before printed calendars, the people of ancient Egypt learned to measure time by watching the sky. Their survival depended on it. Each year, the Nile River rose and flooded its banks. The flood brought rich, black silt that made farming possible. Without it, Egypt would have been only desert. To live along the Nile was to live by its rhythm. Around 3000 to 2600 BCE, during the early dynastic period and the rise of the Old Kingdom, Egyptian scholars and priests developed what is widely known as the first structured 365-day calendar. This was not a rough seasonal guide. It was a fixed civil system, organized and recorded. It shaped government work, temple rituals, farming cycles, and royal authority. At the heart of this system was the star Sirius, known to the Egyptians as Sopdet. Today, we know Sirius as the brightest star in the night sky. Each year, after a period of invisibility, Sirius reappears just before sunrise. This event is called the Heliacal Rising. In ancient Egypt, this rising happened shortly before the Nile flood began. The connection was powerful. When Sirius returned to the dawn sky, the river would soon rise. The timing was not exact every year, but it was close enough to serve as a warning. Farmers prepared their fields. Officials measured water levels. Temples marked the moment with ritual. Sopdet became more than a star. It became a symbol of renewal and order. Evidence for this early calendar appears in inscriptions and administrative records from the Old Kingdom. Pyramid texts carved inside royal tombs from around 2400 BCE mention seasonal divisions and ritual dates. Later temple inscriptions describe months and festival days in detail. These sources show that Egypt had divided the year into 12 months of 30 days each. That created a 360-day year. But the Egyptians knew the solar year was slightly longer, so they added 5 extra days at the end of the year. These were known as epigomenal days. They were considered special, even sacred. According to later myth, these 5 days marked the births of important gods: Osiris, Horus the Elder, Set, Isis, and Nephthys. Though these myths were recorded later, they reflect how deeply the calendar was tied to religion. The result was a 365-day civil calendar. It was simple and regular. Each month had 3 10-day weeks, often called decans. Officials could plan taxes, labor, and building projects with this structure. The state depended on predictability. As Egypt expanded its power during the Old Kingdom and the puzzle of pyramid power, organized timekeeping became essential. Large construction efforts, including pyramid building at Giza during the reigns of Khufu, Khafre, and Menkaure, required careful coordination of labor and resources. The calendar also divided the year into 3 main seasons linked to the Nile. Akhet was the inundation season, when the river flooded. Pere was the growing season, when crops were planted and began to sprout. Shamu was the harvest season. These divisions were practical and rooted in real environmental cycles. They reflected a deep understanding of how land and water worked together. Yet the Egyptian civil calendar had one important flaw. It did not include a leap year. The true solar year is about 365.25 days long. That extra quarter day may seem small, but over time it adds up. Because the Egyptians did not adjust for it, their calendar slowly drifted out of alignment with the seasons. Every 4 years, the calendar would fall behind the solar year by about 1 day. Over centuries, this drift became noticeable. A festival that once marked the flood might eventually occur during the dry season. Still, the Egyptians kept their civil calendar unchanged for thousands of years. They valued its order and stability more than precise seasonal alignment. Modern scholars call this drifting cycle the Sothic cycle, named after the Greek word for Sirius, Sothis. It takes about 1,460 years for the civil calendar to realign with the heliacal rising of Sirius. Ancient records from later periods, including Roman-era texts, mention this long cycle. These references help historians anchor Egyptian chronology. Astronomical ceilings painted inside tombs also offer clues. In the tomb of Senenmut from the 18th dynasty, for example, star charts decorate the ceiling. Though this comes much later than the calendar's creation, it shows a continuing tradition of sky observation. The roots of that tradition stretch back to the early dynastic period. Some scholars ask whether the Egyptian 365-day calendar developed entirely on its own. Others explore connections to earlier African systems. In regions south of Egypt, communities had long observed seasonal star risings and rainfall cycles. Sites such as Nabta Playa, dating back to the 5th millennium BCE, show that sky observation was practiced in northeastern Africa long before the pharaohs. This does not mean the civil calendar was copied directly from one earlier source. There is no written record linking Nabta Playa to dynastic Egypt, but it does show that careful sky watching was already part of life in this region. When we consider the origins of Egypt before the pharaohs, we see a gradual buildup of knowledge. Communities migrating toward the Nile brought traditions, symbols, and practical skills. By the time of Egypt's political unification around 3100 BCE, traditionally linked to Narmer, the need for a shared calendar would have grown. The unification mystery of the first pharaoh involves more than warfare and symbols. It also required administrative tools. A unified state stretching from Upper to Lower Egypt needed common dates for taxation, festivals, and state labor. The civil calendar helped create that unity. It gave Egypt a stable framework of time. Each year began on the first day of Akhet, tied loosely to the rising of Sirius. Even as the calendar drifted, the symbolic link between Sopdet and the flood remained strong in religious thought. Temple records from later periods describe precise festival days for gods in cities like Thebes, Memphis, and Heliopolis. Priests followed the civil calendar closely. Rituals had to be performed on specific days. Offerings were scheduled. Processions moved through streets according to fixed dates. The calendar shaped spiritual life. Government documents written on papyrus also show dated entries. Tax lists, grain deliveries, and labor assignments were recorded by month and day. These papyri, preserved in dry tombs and desert settlements, allow modern historians to reconstruct how the system functioned in daily life. We see workers assigned to crews for specific periods. We see shipments timed around harvest cycles. Despite its drift, the civil calendar proved durable. It lasted through the Old Kingdom, through the collapse of the Old Kingdom and the First Dark Age around 2200 BCE, and into the Middle Kingdom and Egypt's Silent Golden Age. Even when political power weakened, the calendar endured. It became part of Egypt's cultural identity. The drift problem was eventually recognized by Greek and Roman observers. In 238 BCE, during the reign of Ptolemy III, an attempt was made to add a leap day every 4 years. This reform, recorded in the Canopus Decree, did not fully succeed at the time. Only under Roman rule, after 30 BCE, was a leap year system permanently adopted in Egypt. But for over 2,000 years, the original 365-day civil calendar remained unchanged. Its stability may have reflected a deeper Egyptian belief in Ma'at, the concept of cosmic order. Time itself was part of that order. To alter it might have felt disruptive. Today, historians combine archaeology, astronomy, and textual study to understand this system. They examine inscriptions carved into stone. They study papyri written in hieratic script. They calculate ancient star positions using modern software. Through this work, the structure of the Egyptian year becomes clear. What stands out is not just technical skill, but vision. The creation of a fixed 365-day calendar required long observation of the sun and stars. It required abstraction. It required the idea that a year could be measured, divided, and repeated. This was not a simple farming guide. It was a civil framework that shaped one of the world's longest-lasting civilizations. Long before mechanical clocks, Egypt measured time with sky and river. They turned celestial movement into social order. When we think of ancient Egypt, we often picture pyramids and temples. Yet behind those monuments stood something quieter, but just as powerful. A calendar. A system of days and months that guided planting, prayer, taxation, and kingship. The heliacal rising of Sirius still occurs each year. The Nile still flows north to the Mediterranean. But the world that first counted 365 days has long passed. What remains is the idea that time can be organized, recorded, and shared across generations. In that sense, the Egyptian civil calendar was more than a tool. It was the bridge between sky and society. It marked one of humanity's earliest efforts to live not only by nature's rhythm, but by a measured year of our own making. Chapter 3. The Sumerian Calendar. Order in early cities. In the land between the Tigris and Euphrates rivers, time was watched as carefully as water. Southern Mesopotamia, the home of the Sumerians, was a world of mud brick cities rising from flat plains. By around 3000 BCE, cities like Uruk, Ur, Lagash, and Nippur had grown into organized urban centers. Temples towered above houses. Canals carried river water into fields. Trade routes connected distant regions. And above it all, the moon moved steadily across the night sky. For the Sumerians, the moon became the key to measuring time. Unlike Egypt's fixed 365-day civil calendar, early Sumerian timekeeping was based on lunar cycles. A lunar month begins with the first visible crescent after a new moon. This cycle lasts about 29.5 days. The pattern is clear to the naked eye. The moon grows, becomes full, then fades and disappears, only to return again. For early observers, it was a natural clock in the sky. Cuneiform tablets from the late 4th and early 3rd millennium BCE show that Sumerian scribes were already naming months and recording dates. These tablets, discovered in places like Uruk and Ur, include administrative records, temple offerings, and festival lists. Many are simple economic texts, yet they are carefully dated by month and day, proving that a calendar system was already in use. The Sumerian year consisted of 12 lunar months. Each month began with the sighting of the new crescent moon. Priests or temple officials likely observed the sky at dusk, waiting for that thin arc of light. When it appeared, a new month was declared. This direct observation meant that the calendar was tied to visible reality, not abstract calculation. But there was a problem. 12 lunar months add up to about 354 days. That is roughly 11 days shorter than the solar year. Without correction, a purely lunar calendar drifts through the seasons. Over time, a spring festival would occur in winter. Harvest celebrations would fall before crops were ready. In a farming society dependent on seasonal cycles, this drift could not be ignored. Clay tablets from the early dynastic period show evidence that Sumerians understood this mismatch. They began inserting extra months when necessary. This practice is known as intercalation. By adding an additional month every few years, they could bring the lunar calendar back into alignment with the agricultural seasons. We do not have a detailed manual explaining how early Sumerians decided when to insert these extra months. However, temple records suggest that the decision was made by authorities, often priests or city rulers. It may have been based on observation of seasonal changes, such as the timing of barley harvests or river floods. Barley was central to the Sumerian economy. Many tablets record barley rations, barley taxes, and barley storage. The agricultural year needed to stay connected to the calendar year. If months drifted too far, economic planning would suffer. The month names themselves reveal religious meaning. In cities like Ur, months were often named after major festivals or temple rituals. For example, in later Mesopotamian tradition, months included names such as Nisanu and Teshritu, though these come from the Akkadian and Babylonian periods. Earlier Sumerian names varied by city, reflecting local gods and ceremonies. This shows that the calendar was not only practical, it was sacred. Festivals honored deities like Inanna in Uruk, Enlil in Nippur, and Nana, the moon god, in Ur-Nanin. Nana's importance is especially striking. As a lunar deity, he was closely tied to timekeeping. His temple in Ur stood as both religious center and astronomical reference point. Ziggurats, the step temple towers that rose above Sumerian cities, may also have served observational roles. While there is no clear proof that they were built as observatories in the modern sense, their height provided a clear view of the horizon. From these elevated platforms, priests could monitor the moon's phases and possibly the rising and setting of certain stars. Archaeological evidence from the city of Ur, excavated by Sir Leonard Woolley in the 1920s and 1930s, revealed thousands of tablets. Many are administrative documents dated by lunar months and regnal years of kings. These records allow modern scholars to reconstruct the structure of the Sumerian calendar. The Sumerian system was not mathematically perfect. It relied on observation and occasional correction rather than a fixed formula. This meant that accuracy could vary. Some years may have drifted slightly before adjustment was made. Scholars debate how consistent these corrections were across different cities. By the Akkadian period, beginning around 2334 BCE under Sargon of Akkad, and later during the Babylonian era, intercalation became more standardized. Babylonian astronomers eventually developed more precise methods for predicting lunar cycles and scheduling extra months. In this way, the early Sumerian calendar laid the foundation for more advanced systems. The shift from simple lunar tracking to attempts at solar consistency marks an important transition in human thought. At first, the moon alone guided the month, but as cities grew and administration became more complex, awareness of the solar year increased. Seasonal drift was not only a farming issue, it affected religious timing and political authority. Kings often tied their legitimacy to proper ritual performance. If festivals occurred at the wrong season, it could be seen as disorder. In a world where divine favor mattered deeply, maintaining cosmic balance was part of governance. Unlike the Egyptian civil calendar, which was fixed and allowed to drift slowly, the Sumerian approach was flexible. It accepted drift as natural, but corrected it when needed. This reflects a different mindset. Instead of imposing a rigid structure on the year, the Sumerians adjusted in response to observation. Cuneiform texts from later Babylonian scholars show a growing interest in predicting lunar eclipses and planetary movements. These developments were built on centuries of earlier lunar observation. The roots lie in Sumerian cities where priests first watched for the crescent moon. Some historians compare this process to the gradual evolution of urban order itself. Early villages became organized cities. Simple record-keeping became writing. Basic lunar tracking became a managed calendar. In each case, complexity grew from practical need. It is important to note that the Sumerian calendar was not purely solar. It never abandoned the moon as its primary marker. Yet over time, solar awareness increased. The need to keep months tied to harvest and flooding cycles pushed authorities to think beyond the moon's simple rhythm. Scholars still debate how accurate early intercalation was. Because records from the 3rd millennium BCE are incomplete, it is difficult to calculate long-term precision. Some evidence suggests that corrections were sometimes delayed. Other texts imply careful management. What is clear is that the Sumerians recognized the problem of drift. They did not ignore it. Their solution was practical, even if imperfect. They inserted an extra month when needed, keeping ritual and agriculture roughly aligned with the sun. The influence of this system extended far beyond Sumer. The Babylonian calendar, which later influenced Hebrew and other Near Eastern calendars, inherited the lunar base and intercalation method. Even today, some religious calendars use similar principles. When we look at early Mesopotamia, we often focus on writing, law codes, and monumental architecture. Yet behind these achievements stood a quieter innovation, a way to organize time in growing cities. In the narrow streets of Uruk, merchants needed dates for contracts. In the temple courts of Nippur, priests needed fixed days for offerings. In the fields outside Lagash, farmers needed to know when to sow barley. The moon offered a visible guide, but the sun demanded attention too. The Sumerian calendar represents a bridge between sky and city. It shows how early urban societies moved from simple observation to structured timekeeping. It reveals a growing awareness that nature's cycles were complex and required adjustment. As night fell over the plains of Mesopotamia, priests looked for the first silver crescent. In that thin line of light, they saw the start of a new month, but behind that moment lay deeper understanding. They knew the seasons could slip. They knew correction was needed. In this balance between moon and sun, between observation and adjustment, early cities found order. The Sumerian calendar was not perfect. It did not freeze time into a fixed year. Instead, it adapted year after year, reflecting a civilization learning to measure both heaven and earth. And in that careful watching of the sky, the foundations of later astronomical science quietly began. Chapter 4. The Maya Long Count. A precise year across the ocean. Thousands of miles from the Nile and the plains of Mesopotamia, another civilization was also watching the sky with remarkable care. In the tropical forests of Mesoamerica, the ancient Maya built cities of stone and developed one of the most precise calendar systems in the ancient world. Their understanding of time was not simple or symbolic. It was mathematical, recorded, and deeply connected to both ritual and daily life. By the first millennium BCE, early Maya communities were already tracking cycles of days. By the Classic period, between 250 and 900 CE, cities like Tikal in present-day Guatemala, Palenque in southern Mexico, and Copan in Honduras were carving detailed dates into stone monuments. These inscriptions reveal a complex calendar system built on careful astronomical observation. The Maya used more than one calendar at the same time. One was the Hab, a 365-day solar calendar. Another was the Tzolk'in, a 260-day ritual cycle. Together, these calendars formed what scholars call the calendar round. But beyond these repeating cycles, the Maya created something even more ambitious: the long count, a system that recorded dates across vast stretches of time. The Hab calendar was structured in a clear pattern. It consisted of 18 months, each with 20 days. That created 360 days. To complete the solar year, the Maya added 5 extra days at the end, known as Wei-eb. These 5 days were considered spiritually dangerous or unstable. Ritual precautions were often taken during this short period. Unlike the Egyptian civil calendar, which slowly drifted because it lacked leap years, the Hab was slightly shorter than the true solar year. Yet the Maya were aware of the difference. Evidence suggests they understood the solar year to be about 365.242 days long, very close to the modern calculation of 365.2422 days. They did not create a leap year system like the later Roman calendar, but their astronomical tables show advanced awareness of solar cycles. The Tzolk'in operated alongside the Hab. It combined a cycle of 20 named days with a cycle of 13 numbers. Each day had both a name and a number, creating 260 unique combinations before repeating. The origin of the 260-day cycle is still debated. Some scholars connect it to agricultural rhythms, others to human gestation periods, and some to solar zenith passages in southern Mesoamerica. When the 365-day Hab and the 260-day Tzolk'in were combined, a unique calendar round date would not repeat for 52 Hab years. This 52-year cycle was significant in Mesoamerican cultures. It represented a full turning of sacred and solar time together. But the long count went further. It recorded time as a continuous count of days since a mythological starting point. According to most inscriptions, this base date corresponds to August 11th, 3114 BCE in the modern Gregorian calendar. The Maya did not see this as the literal creation of the universe in a scientific sense. It was a symbolic beginning, marking the start of the current era in their cosmology. Long count dates were written in units called baktuns, cottons, tons, unals, and kins. 1 kin equaled 1 day. 20 kins made a unal. 18 unals made a ton, roughly 360 days. 20 tons formed a katun. 20 katuns made a baktun. This structure allowed the Maya to record dates thousands of years in the past or future. Monuments in Tikal, Palenque, and Copan display these long-count dates clearly carved into stone stelae. These stelae often commemorate the accession of kings, important rituals, or major events. Thanks to the work of modern epigraphers such as Tatiana Proskoryakov and Yuri Norosov, much of the Maya script has been deciphered. We now know that many inscriptions record real historical events tied to precise calendar dates. The Dresden Codex, one of the few surviving Maya books, contains detailed astronomical tables. Created before the Spanish conquest but preserved in Europe, it includes calculations for Venus cycles and eclipse patterns. The Venus table tracks the planet's 584-day synodic cycle with impressive accuracy. The Maya associated Venus with warfare and divine power. Its appearance as the morning star was often linked to significant events. Solar observations were equally important. In some Maya cities, temples and pyramids are aligned with solar events. At sites like Chichen Itza, later in the post-classic period, the pyramid known as El Castillo creates a shadow effect during equinoxes. Earlier classic sites also show architectural alignments that may correspond to solstices or zenith passages, when the sun passes directly overhead and casts no shadow at midday. In the lowland Maya region, zenith passages occur twice a year. These events were closely tied to planting cycles. Tracking them helped farmers know when to begin preparing fields. The calendar was not abstract, it shaped survival. Much of what we know about Maya timekeeping survived by chance. In the 16th century, Spanish colonizers destroyed countless Maya books, seeing them as pagan. Bishop Diego de Landa famously ordered the burning of manuscripts in Yucatan in 1562. Only 4 pre-Columbian codices are known to survive today: the Dresden, Madrid, Paris, and the Grolier Codex, now often called the Maya Codex of Mexico. Because so many records were lost, modern scholars had to reconstruct the calendar system from surviving monuments and fragments. In the 19th and 20th centuries, archaeologists carefully documented stelae at Köpen and Tikal. By comparing repeating patterns of glyphs and dates, researchers began to understand the structures of the long count. One major breakthrough came when scholars realized that certain glyphs represented numbers in a base 20 system. Dots stood for ones. Bars stood for fives. A shell symbol marked 0. The use of 0 as a placeholder was an advanced mathematical concept. It allowed the Maya to calculate large spans of time with clarity. Despite this precise system, modern misconceptions have often distorted Maya calendar history. In popular culture, the end of the 13th Baktun on December 21, 2012, was described as a prediction of the end of the world. This idea was not based on Maya texts. In reality, inscriptions such as Monument 6 at Tortuguero mention the completion of the 13th Baktun as a significant anniversary, not a cosmic ending. For the Maya, cycles ending were moments of renewal, not destruction. Their calendar was cyclical and continuous. Just as a new Katun followed the previous one, a new Baktun began after the 13th was complete. The system was designed to move forward indefinitely. Today, archaeologists continue to study inscriptions across Mesoamerica. LiDAR technology has revealed hidden structures beneath jungle canopies, expanding our understanding of Maya urban planning. Each new monument uncovered often carries carved dates that add detail to the historical timeline. What stands out in the Maya system is its balance between ritual and astronomy. The Hab tracked the solar year, the Solkan structured spiritual life, the long count anchored history in deep time. Together they formed a framework that linked human action to cosmic order. In the plazas of Tikal, rulers stood before carved stelae that recorded their reign in precise numerical form. In Palenque, inscriptions on temple walls described royal events tied to exact dates. At Copan, hieroglyphic stairways listed sequences of rulers alongside long count calculations. These were not vague mythic records. They were historical statements measured in days. Across the ocean from Egypt and Mesopotamia, the Maya reached similar conclusions in their own way. The sun, the moon, Venus, and the turning of seasons could be counted. Time could be structured and preserved in stone. Even after colonial destruction, the surviving evidence reveals a civilization deeply committed to understanding celestial order. Their calendar was not just a tool, it was a bridge between sky, state, and spirit. When we look at the carved dates on Maya monuments, we see more than numbers. We see a culture that believed time itself was sacred measurable, and eternal. And in that belief, carved across centuries of stone, the Maya left one of the most precise ancient records of the year the world has ever known. Chapter 5, Göbekli Tepe. Time before cities. On a limestone ridge in southeastern Turkey, not far from the modern city of Şanlıurfa, stands one of the oldest monumental sites ever discovered. Today it is known as Göbekli Tepe. Its name means potbelly hill in Turkish. From a distance, it looks like a gentle rise in the landscape. But beneath that hill lies a structure that changed how we understand the beginnings of organized human life. Göbekli Tepe dates back to around 9,600 BCE. That is more than 11,000 years ago. It was built long before pottery, long before metal tools, and thousands of years before cities like Uruk or the pyramids of Egypt. At that time, humans in the region were hunter-gatherers. Farming had not yet fully developed. Permanent urban settlements did not exist. The site was first noted in the 1960s during a survey by Turkish and American researchers. At the time, it was thought to be a simple medieval cemetery. But in 1994, German archaeologist Klaus Schmidt began new excavations. What he uncovered surprised the world. Beneath the soil were massive circular enclosures made of stone. At the center of each enclosure stood two tall T-shaped pillars, some reaching over 5 meters high and weighing several tons. Around them were smaller pillars arranged in a ring. These pillars were carved with reliefs of animals: foxes, snakes, wild boars, vultures, and scorpions. Some also show abstract symbols and stylized human features. Radiocarbon dating of organic material from the site places the earliest construction around 9,600 BCE, during what archaeologists call the pre-pottery Neolithic A period. This is long before formal calendars are known to have existed. There are no written records at Göbekli Tepe. There are no inscriptions explaining its purpose. What we know comes from excavation data and careful study of the stone structures. The T-shaped pillars are especially striking. Many scholars believe they represent stylized human forms. Some pillars have carved arms and hands along their sides, with belts and loincloths visible in relief. The tops of the pillars form a horizontal crosspiece, creating the T-shape. These features suggest that the pillars may symbolize human or supernatural beings standing within the enclosures. The enclosures themselves were built in circular layouts, with stone walls connecting the outer ring of pillars. Floors were carefully prepared. In some cases, terrazzo-like surfaces were created using crushed limestone. This required skill and planning. Even though the builders were hunter-gatherers, they were capable of large-scale, coordinated labor. The site was not a settlement in the usual sense. Archaeologists have found very few signs of domestic life, such as hearths, storage areas, or everyday housing structures in the earliest layers. Instead, Göbekli Tepe appears to have been a ritual center. People may have gathered there seasonally for ceremonies, feasts, or communal events. Animal bones found at the site support this idea. Remains of gazelle, wild cattle, and other game animals suggest large-scale consumption. These were not small family meals. They appear to have been organized gatherings. Because the site predates farming, Göbekli Tepe challenges older ideas that agriculture led directly to organized religion and monumental architecture. Here it seems that ritual activity may have come first. Some scholars even argue that the need to gather and feed large groups could have encouraged early experimentation with plant cultivation. But what about timekeeping? Did the builders of Göbekli Tepe track the seasons? There is no confirmed 365-day calendar at the site. There are no carved month names, no clear solar markers, no written records of dates. Mainstream archaeology remains cautious. However, some researchers have proposed that certain alignments of the enclosures may relate to celestial events. Orientation studies show that the circular structures are not randomly positioned. Many enclosures appear aligned roughly toward the southeast. Some scholars suggest this direction could correspond to the rising of certain stars or to the position of the sun at particular times of year. One hypothesis proposed by researchers, including Julian, suggests that some pillars may align with the rising of the star Sirius around 9000 BCE. According to this theory, the appearance of Sirius after a long absence in the sky may have held symbolic importance. However, this idea remains debated. Precise astronomical reconstruction for such an early date is complex. The margins of error are significant. Other researchers have looked at possible solstice alignments. The summer and winter solstices mark the longest and shortest days of the year. In many later ancient cultures, these events were carefully observed. It is reasonable to ask whether early ritual centers like Göbekli Tepe required awareness of seasonal cycles. Seasonal awareness would have been important for hunter-gatherers. Animal migrations, plant growth, and weather patterns all follow seasonal rhythms. Even without a formal calendar, people would have needed to know when certain resources were available. Yet awareness of seasons does not equal a structured calendar. Archaeologists stress that while alignments are possible, there is no clear evidence that Göbekli Tepe functioned as an astronomical observatory in the way later sites sometimes did. The animal carvings themselves may hold symbolic meaning connected to cycles of nature. For example, snakes and scorpions could represent danger or transformation. Vultures appear frequently and may have been linked to death rituals. Some scholars interpret certain reliefs as scenes involving headless figures and birds, possibly connected to burial practices. Still, these interpretations are cautious. Without written explanation, symbolism can only be inferred through comparison with other Neolithic sites in the region. What is firmly established is the scale and organization of the site. Moving multi-ton pillars without metal tools required planning, manpower, and shared purpose. The people who built Göbekli Tepe were capable of cooperation on a level once thought impossible for hunter-gatherers. Around 8000 BCE, the site was deliberately buried. Enclosures were filled with rubble and debris. New structures were built on top. Eventually, the entire hill became a layered monument hidden beneath earth. The reason for this burial is not fully understood. It may have been part of ritual closure. The fact that Göbekli Tepe was intentionally covered preserved it for thousands of years. When modern excavations began, the carvings were still sharp, protected from erosion. In the broader story of human timekeeping, Göbekli Tepe represents a stage before formal calendars. It shows that monumental ritual architecture existed long before cities and written records. It suggests that shared belief systems may have required coordination across seasons. While we cannot confirm a 365-day system here, we can imagine that gatherings at the site likely followed recurring patterns. People may have returned at certain times of year, guided by environmental signs or celestial cues. Even without numbers carved into stone, time was present in the rhythm of movement and memory. Mainstream archaeological consensus remains careful. Göbekli Tepe is not presented as proof of advanced lost astronomy. It is understood as a pre-pottery Neolithic ritual complex built by organized hunter-gatherers. Astronomical hypotheses are explored, but they remain secondary to confirmed findings. What makes the site powerful is not speculation, but certainty. It proves that large-scale symbolic architecture predates cities by thousands of years. It shows that communal identity and ritual planning existed at the dawn of settled life. Standing among the pillars today, one feels the weight of deep time. The carvings of animals still look outward across the plain. The T-shaped stones still rise toward the sky. Göbekli Tepe reminds us that before formal calendars, before months and numbered years, humans were already gathering to mark something larger than themselves. Whether that something was tied to stars, seasons, or shared belief, it required memory and repetition. Time even then mattered. Long before written dates and structured years, people stood on that ridge and looked toward the horizon. They carved stone, they returned again and again. In that repetition, we see the earliest roots of humanity's effort to give shape to time itself. Chapter 6. Stonehenge, Britain's solar monument. On a windswept plain in southern England, massive stones rise from the earth in a pattern that has drawn attention for centuries. This is Stonehenge. Located in Wiltshire, not far from the modern city of Salisbury, it stands as one of the most studied prehistoric monuments in the world. Built in several phases between roughly 3000 and 2000 BCE, Stonehenge continues to shape how we think about ancient timekeeping, ritual, and community. At first glance, Stonehenge appears simple. Large upright stones support horizontal lintels, forming circles and horseshoe shapes. But beneath this visible structure lies a complex history of construction, rebuilding, and redesign. Modern archaeology has revealed that Stonehenge was not built all at once. It evolved over 1,000 years. The earliest phase, around 3000 BCE, did not include the towering stones we see today. Instead, there was a circular ditch and bank about 110 meters across. This earthwork enclosure contained a ring of pits known as the Aubrey Holes, named after the 17th century antiquarian John Aubrey. Excavations have shown that many of these pits once held timber posts and later cremated human remains. Radiocarbon dating of cremated bones found in these early layers places some burials between 3000 and 2500 BCE. This suggests that Stonehenge began as a ceremonial and funerary site. It was a place where the dead were honored and remembered. Around 2500 BCE, the monument entered a new phase. Massive sarsen stones, some weighing over 20 tons, were transported from the Marlborough Downs, about 20 miles away. Smaller blue stones were brought from the Preseli Hills in southwest Wales, over 140 miles distant. The movement of these stones required organization, manpower, and planning on a large scale. The sarsens were shaped carefully. Mortise and tenon joints were carved into their tops, allowing lintels to fit securely in place. This woodworking style technique applied to stone shows remarkable skill. The builders were not random experimenters, they were experienced engineers. What makes Stonehenge especially significant is its alignment with the sun. If one stands at the center of the monument on the summer solstice, around June 21st, the sun rises in line with the heel stone, an outlying upright stone positioned to the northeast. At the winter solstice around December 21st, the sun sets in alignment with the central axis in the opposite direction. These alignments are not accidental. Archaeologists and astronomers have confirmed them through precise measurements in computer simulations. The axis of the monument clearly marks the path of the sun at these key points in the year. Because of this, some researchers suggest Stonehenge functioned as a solar calendar. It could have marked the annual cycle, signaling the longest and shortest days of the year. In agricultural societies, such knowledge was valuable. Knowing when days began to lengthen again after winter could carry deep symbolic meaning. However, most archaeologists are cautious about calling Stonehenge a full calendar. While the solstice alignments are clear, there is no evidence of day-by-day tracking like a 365-day system. Instead, Stonehenge appears to mark turning points in the solar year, not every passing day. Recent research has deepened our understanding of how the monument functioned within its landscape. Ground-penetrating radar and magnetometry surveys have revealed additional features surrounding the stone circle. Nearby, at a site called Durrington Walls, archaeologists uncovered remains of large wooden structures and evidence of feasting. Excavations at Durrington Walls, led by researchers such as Mike Parker Pearson, suggest that this settlement may have housed people involved in building Stonehenge. Animal bones found there show signs of large communal meals, especially around winter. Isotopic analysis of pig remains indicates that animals were brought from distant regions, suggesting gatherings that drew people from across Britain. Isotopic studies of human remains buried at Stonehenge also provide insight. By analyzing strontium isotopes in teeth, scientists can determine where a person grew up. Some individuals buried at the site appear to have come from Western Britain, possibly even from areas near the Preseli Hills where the bluestones originated. This supports the idea that Stonehenge was not a local shrine, but a monument with wide cultural importance. The winter solstice alignment may have been especially significant. While the summer sunrise is visually dramatic today, evidence from animal remains and settlement patterns suggests that midwinter gatherings were central. In a farming society, winter was a time when livestock were slaughtered and food was shared. The setting sun on the shortest day may have symbolized both an ending and a promise of return. Unlike later historical societies, the builders of Stonehenge left no written records. There are no inscriptions explaining their purpose. What we have are stones, bones, tools, and the landscape itself. Through careful excavation and analysis, archaeologists piece together patterns. Some earlier theories propose that Stonehenge was an advanced astronomical observatory capable of predicting eclipses. These ideas, popular in the 20th century, have largely been rejected by mainstream scholars. While the monument reflects awareness of solar cycles, there is no strong evidence that it tracked complex planetary movements. What is clear is that Stonehenge links ritual and timekeeping. The solstice alignment suggests intentional design connected to the sun's movement. The burial evidence shows that ancestors were central to its meaning. The nearby settlements indicate large communal gatherings. The monument also changed over time. After 2000 BCE, construction slowed. Some stones were rearranged, others were removed. The site continued to be visited into the Bronze Age, but its main building phase ended. Today, modern technology continues to reveal new details. Laser scanning and digital modeling allow researchers to reconstruct how the monument would have looked when complete. Excavation records from earlier digs are reanalyzed with improved methods. Each new study refines our understanding. Stonehenge stands within a broader prehistoric landscape filled with barrows, avenues, and other monuments. It was not isolated. It was part of a network of ritual sites across southern Britain. This landscape itself may have functioned as a ceremonial map tied to cycles of life and death. When we consider whether Stonehenge was a solar calendar, the answer may lie somewhere between strict measurement and symbolic marking. It did not count every day of the year, but it clearly marked key solar moments. Those moments likely structured communal gatherings and reinforced shared identity. On the summer solstice today, thousands of people gather to watch the sun rise over the Heelstone. Though separated by millennia from the original builders, they stand in the same alignment. The light breaks over the horizon in the same way it did 4,000 years ago. This continuity is powerful. It reminds us that even without writing or formal calendars, prehistoric communities observed the sky with care. They shaped stone to match celestial patterns. They gathered at predictable times of year, linking human ceremony to cosmic rhythm. Stonehenge is not just a circle of stones, it is a record of attention. It shows that ancient Britain's communities understood the importance of seasonal turning points. Through labor and design, they fixed those moments into the landscape. In doing so, they created a monument that bridges ritual and astronomy, a place where the path of the sun meets the memory of the dead, a structure that does not count every day, but honors the great markers of the year. And in that balance between ceremony and solar alignment, Stonehenge stands as Britain's enduring monument to time. Chapter 7. The Olmec and Early Mesoamerican Timekeeping. Long before the rise of the great Maya cities, another civilization shaped the cultural foundations of Mesoamerica. Along the Gulf Coast of present-day Mexico, in the humid lowlands of Veracruz and Tabasco, the Olmec built ceremonial centers, carved massive stone heads, and developed symbols that would echo through the later cultures. Flourishing roughly between 1500 and 400 BCE, the Olmec are often called the mother culture of Mesoamerica. While that label is debated, there is little doubt that their influence was deep. Among the ideas that may have begun in Olmec society is an early understanding of cyclical time. The Olmec left no surviving books. The tropical climate did not preserve organic materials well. What remains are monumental stone carvings, earthen platforms, buried offerings, and scattered inscriptions. From these fragments, archaeologists attempt to understand how the Olmec viewed the world. San Lorenzo, one of the earliest Olmec centers, reached its peak around 1200 BCE. Massive basalt heads, some weighing over 20 tons, were transported from distant quarries and carved into portraits of rulers. These heads suggest organized leadership and long-distance planning. Nearby at La Venta, a later ceremonial center, active around 900 to 400 BCE, large earthen pyramids and stone altars were constructed with careful alignment. The orientation of some Olmec sites hints at astronomical awareness. At La Venta, the main ceremonial complex appears slightly tilted from true north, aligned roughly 8 degrees west of north. Some researchers propose that this orientation may correspond to the setting of certain stars or to solar positions on specific dates. However, such interpretations remain cautious. While alignments are measurable, their exact meaning is debated. Unlike the later Maya, the Olmec did not leave clear, lengthy date inscriptions. Yet early glyph-like symbols appear on monuments and portable objects. One of the most important discoveries in this field is the Cascajal block, a stone slab found in Veracruz and dated to around 900 BCE. It contains a sequence of carved symbols that some scholars interpret as the earliest known writing system in the Americas. The Cascajal block does not display an obvious calendar date. However, its existence suggests that symbolic recording systems were developing during the Olmec period. Writing and calendar systems often evolve together because both involve counting, sequencing, and marking time. Another key artifact is Stela 1 from La Venta. Though heavily weathered, it shows a figure emerging from a cave-like opening surrounded by symbols. While not clearly a calendar text, it reflects a complex symbolic tradition that later Mesoamerican cultures would expand. Some scholars argue that elements of the 260-day ritual calendar, later known among the Mayas as Tzolk'in, may have roots in Olmec times. The 260-day cycle appears across many Mesoamerican cultures, including the Zapotec and later the Aztec. Its widespread use suggests deep origins. The earliest confirmed long count date appears much later, on Stela C from Trezopodes, dated to 31 BCE. Trezopodes was a site influenced by Olmec culture, but active after the main Olmec period had ended. The presence of an early long count inscription there raises questions about cultural continuity. Did the Olmec develop an early version of the system, or did later groups build on shared regional traditions? Archaeologists are careful not to claim more than evidence allows. There is no clear 365-day Hobbes-style calendar documented directly in Olmec inscriptions. There are no fully deciphered Olmec month names. What we see instead are hints of structured time awareness embedded in ritual architecture and symbolic art. San Lorenzo and La Venta both feature carefully planned ceremonial layouts. Large plazas, raised platforms, and aligned monuments suggest gatherings at specific times. Agricultural cycles in the Gulf Coast region would have required knowledge of rainy and dry seasons. Maize cultivation was central to Olmec life. Seasonal timing mattered for planting and harvest. It is reasonable to assume that the Olmec tracked the movement of the sun and possibly the moon. Across Mesoamerica, solar zenith passages, when the sun stands directly overhead, were significant agricultural markers. In the Olmec heartland, such events occur twice a year. These solar positions may have been observed even if not formally recorded in surviving inscriptions. Another important piece of evidence comes from the Epi-Olmec period, which followed the decline of the main Olmec centers. During this time, more explicit inscriptions appear, including early examples of the Isthmian script. Some of these later texts include calendar-style dates that resemble the long count. This suggests that the intellectual foundations of later calendar systems were already forming in the region. The spread of calendar knowledge in Mesoamerica likely occurred through trade and cultural exchange. The Olmec maintained connections with highland and lowland communities across what is now Mexico and Guatemala. Jade, obsidian, and basalt were transported over long distances. Along with goods, ideas traveled. Iconography found at distant sites often reflects Olmec artistic influence. Motifs such as the war-jaguar figure, composite creatures, and certain symbolic patterns appear beyond the Gulf Coast. This cultural network could have carried early concepts of cyclical time and ritual counting. Scholars debate whether the Olmec should be seen as direct inventors of later Mesoamerican calendars or as participants in a broader regional development. Some argue that calling them the mother culture oversimplifies complex interactions among early societies. Others emphasize their early date and widespread influence. Modern research relies on excavation data, radiocarbon dating, and comparative analysis. Advances in remote sensing and LiDAR scanning are revealing new structures beneath dense vegetation. Each discovery adds context to Olmec ceremonial planning. One striking aspect of Olmec culture is its focus on cyclical themes in art. Repeated imagery of transformation, duality, and renewal suggests a worldview centered on cycles rather than linear time. This philosophical orientation aligns with later Mesoamerican calendar systems, which were deeply cyclical. When the Maya later developed the Hobbes, Tzolk'in, and long count systems, they operated within an intellectual tradition that already valued measured time and ritual cycles. Whether directly inherited from the Olmec or shaped through shared development, the foundation was in place. Spanish colonial destruction in later centuries erased many written records from Mesoamerica, especially among the Maya and Aztec. Because the Olmec lived much earlier and left fewer written materials, reconstructing their calendar knowledge is especially challenging. Archaeologists must rely on stone carvings, architectural alignment, and indirect evidence. What emerges is not a fully formed 365-day system, but an early stage in the evolution of timekeeping. The Olmec appear to have understood that time moved in repeating patterns. Their ceremonial centers likely hosted rituals tied to seasonal changes. Their symbolic carvings hint at counting and sequencing. Standing among the remains of Nabta today, one sees earthen mounds rising from flat terrain. Once these mounds supported structures that marked social and spiritual life. People gathered there, perhaps at specific times of year, guided by sun and season. The story of early Mesoamerican timekeeping does not begin with complete calendars carved in stone. It begins with communities observing the sky, organizing ritual space, and creating symbols to mark recurring events. The Olmec were part of that beginning. Though we cannot point to a single Olmec tablet and read a full calendar date, we can trace a path from their monuments to later, more detailed systems. The continuity of cyclical thought across centuries suggests deep roots. In that sense, the Olmec stand at the dawn of measured time in the Americas, not yet counting baktuns or naming months, but already shaping a worldview where the turning of seasons and the repetition of ritual were central. Their stone heads still face outward across the landscape. Their platforms still rise above the plains. And within those silent forms lies the early pulse of a calendar tradition that would later reach extraordinary precision. Before the Maya carved long sequences of dates, before codices recorded Venus cycles, there were the Olmec, watching, building, and beginning to measure the repeating patterns of the world around them. Chapter 8. Ancient China's Early Solar Calculations. In the broad river valleys of northern China, long before the Great Wall or the imperial capitals of later dynasties, early Chinese societies were already watching the sky with care. The Yellow River Basin, often called the cradle of Chinese civilization, supported farming communities that depended on seasonal rhythms. Like other ancient cultures, they needed to know when to plant and when to harvest. Over time, this need led to the development of one of the world's most enduring calendar traditions. By the time of the Shang dynasty, which ruled from around 1600 to 1046 BCE, Chinese elites were already recording astronomical observations. Our knowledge of this period comes in part from oracle bones, turtle plastrons, and ox scapulae used in divination. These bones were inscribed with questions posed to royal ancestors or spirits. Many of those questions mentioned dates, lunar phases, and celestial events. The Shang calendar was lunisolar. Months were based on the phases of the moon, beginning with the new moon. A lunar month lasts about 29.5 days, so months alternated between 29 and 30 days. 12 lunar months make about 354 days, which is shorter than the solar year. Without correction, the calendar would drift out of step with the seasons. The Shang court was aware of this problem. Oracle bone inscriptions suggest that officials monitored seasonal markers carefully. Agricultural rituals and royal ceremonies had to align with the proper time of year. When drift became noticeable, an extra month was inserted. This intercalary month brought the lunar calendar back into alignment with the solar cycle. These inscriptions show that calendar management was a matter of state importance. The king himself was often involved in divination about timing. Questions recorded on oracle bones include whether a ritual should be performed on a certain day, or whether weather conditions would affect crops. Timekeeping was not abstract. It was tied to survival and political authority. After the fall of the Shang, the Zhou dynasty rose to power around 1046 BCE. During the Western Zhou period, calendar regulation became more formalized. Bronze inscriptions from this era record events with precise dating systems, including references to months and cyclical day names. One important feature of early Chinese timekeeping was the use of the sexagenary cycle, a system combining 10 heavenly stems and 12 earthly branches to create a repeating cycle of 60 days. Each day received a unique combination, allowing precise identification within a repeating pattern. This system, which originated in the Shang period, remained in use for thousands of years. Solar awareness deepened during the Zhou dynasty. Officials tracked solstices and equinox like seasonal markers to maintain agricultural order. The winter solstice, when daylight begins to increase again, was especially significant. Later classical texts describe it as a moment of renewal and balance. While early Chinese calendars were not initially fixed at exactly 365 days, scholars recognized the length of the solar year with increasing precision. By the late Zhou period, astronomers understood that the solar year was slightly longer than 365 days. Though methods varied over centuries, their calculations gradually improved. The concept of dividing the year into 24 solar terms, known as jieki, also developed in early China. These solar terms mark specific positions of the sun along the ecliptic and were closely tied to agricultural tasks. For example, certain terms signaled the time for planting millet or harvesting wheat. Though the system was refined later, its foundations lie in early observational practices. Archaeological evidence from the site of Taosi, dating to around 2300 BCE in the late Neolithic period, suggests even earlier solar awareness. Excavations have revealed what some researchers interpret as an ancient observatory structure aligned with sunrise positions at certain times of year. While debate continues over the exact function of these features, they indicate that careful solar observation predates the Shang dynasty. Historical texts compiled much later, such as the Book of Documents and the Records of the Grand Historian by Sima Qian, describe earlier calendar reforms in astronomical offices. Although these texts were written centuries after the events they describe, they preserve traditions of systematic sky watching that likely have deep roots. By the time of the Eastern Zhou period, especially during the spring and autumn and Warring States eras, astronomical study became more specialized. Officials known as Shi were responsible for observing celestial movements and reporting them to the court. Eclipse records from this period have been compared with modern astronomical calculations and found to be surprisingly accurate. The insertion of leap months became more regularized over time. Instead of waiting for noticeable seasonal drift, scholars developed rules for intercalation. Though not yet based on modern mathematical formulas, these adjustments reflected an increasing desire for solar consistency within a lunar framework. Unlike a purely solar calendar with fixed 365 days, the Chinese system remained fundamentally lunisolar. Months still began with the new moon. Festivals were scheduled according to lunar dates, yet the solar year remained the anchor that prevented seasonal confusion. One example of careful record-keeping appears in the Bamboo Annals, a chronicle that preserves dates of events from early dynasties. Though parts of the text are fragmentary and subject to scholarly debate, it reflects a long tradition of linking historical events to structured time cycles. Modern historians reconstruct early Chinese calendars through a combination of archaeology and textual study. Oracle bones, bronze inscriptions, bamboo slips, and later historical works are analyzed together. Astronomical references are checked against calculated positions of the sun and moon to confirm dating accuracy. It is important to separate documented evidence from mythic origin stories. Later Chinese tradition sometimes attributes calendar invention to legendary figures such as the Yellow Emperor. However, there is no archaeological proof linking such myths directly to early calendar systems. What we have instead is gradual development visible in inscriptions and artifacts. The connection between calendar regulation and political authority is especially clear. In ancient China, the right to issue a calendar was linked to the mandate of heaven, the belief that a ruler's legitimacy depended on cosmic harmony. If the calendar failed to match the seasons, it could be seen as a sign of disorder. Accurate timekeeping reinforced royal power. Agriculture in the Yellow River Basin depended on predictable seasonal changes. Flooding, planting, and harvesting all required careful timing. A drifting calendar could cause economic harm. Thus, the insertion of leap months was not merely technical. It was a matter of state stability. By the Han Dynasty, beginning in 206 BCE, Chinese astronomers achieved even greater precision. The Taichu calendar reform of 104 BCE established more accurate calculations of the solar year, but these later achievements built upon centuries of earlier observation. When we look back to the Shang and Zhou periods, we see the beginnings of this tradition. Oracle bones record lunar dates and celestial events. Bronze inscriptions preserve month names and ritual timing. Archaeological sites reveal structures aligned with solar positions. Across the centuries, early Chinese scholars moved from simple lunar tracking to sophisticated lunisolar coordination. They did not fix the year at exactly 365 days at first. Instead, they balanced moon and sun through intercalation. This flexibility allowed them to keep ritual and agriculture aligned with nature's cycles. In the quiet act of observing a new moon or marking the winter solstice, they were shaping a system that would guide Chinese civilization for millennia. Time was not merely counted, it was harmonized. Ancient China's early solar calculations were not sudden inventions. They were the result of patient watching, careful recording, and gradual refinement. From oracle bone divinations to formalized leap months, the path was steady. In that long effort to keep seasons and months in balance, early Chinese civilizations demonstrated deep awareness of the sun's journey across the sky. And in doing so, they built one of the most enduring calendar traditions in human history. Chapter 9. The Andean Solar Observatories. High in the coastal desert of northern Peru, where dry hills rise between the Pacific Ocean and the Andes, stands a line of stone towers stretching across a ridge. From a distance, they look simple, almost like broken walls. But when seen from the right viewpoint, they reveal one of the most remarkable solar observatories in the ancient world. This site is known as Changkilo. Changkilo dates to around 300 BCE, during what archaeologists call the late formative period in the Andean region. It is much later than the earliest known calendar systems in Egypt or Mesopotamia, yet it represents an independent and highly sophisticated effort to track the movement of the sun. Here in Peru, thousands of miles from Africa or Eurasia, people built a structure that could mark the solar year with striking precision. The heart of Changkilo is a row of 13 towers arranged along the crest of a low hill. The towers are evenly spaced and connected by low walls, forming a jagged silhouette against the sky. On either side of this ridge are two observation points. From these points, a viewer can watch the sun rise or set along the line of towers throughout the year. Archaeological excavation at Changkilo began in the early 20th century, but detailed study accelerated in the late 20th and early 21st centuries. Peruvian archaeologist Ibn Gezi, along with British archaeoastronomer Clive Ruggles, conducted careful surveys of the site. Using precise measurements and astronomical modeling, they demonstrated that the towers align closely with the sun's changing position on the horizon over the course of a year. From the western observation point, the sun rises at the far left of the tower line during the June solstice, the winter solstice in the southern hemisphere. As the days pass, the rising position shifts gradually along the towers. By the December solstice, the summer solstice in Peru, the sun rises at the far right end of the line. The towers divide the horizon into intervals that correspond closely to the days of the year. Unlike monuments that mark only solstices or equinoxes, Changkilo allows near daily tracking. A careful observer standing at the designated viewing point could estimate the date within a few days, simply by noting the sun's position relative to the towers. This makes Changkilo one of the clearest archaeological examples of a solar calendar in the ancient world. Radiocarbon dating of materials found at the site places its main construction phase around the 4th to 3rd centuries BCE. Pottery fragments, architectural style, and stratigraphic analysis support this timeline. The site includes more than just the towers. Nearby are fortified structures, plazas, and storage areas, suggesting that Changkilo was part of a larger ceremonial and administrative complex. The region around Changkilo is arid, but river valleys cut through the desert, supporting agriculture. Crops such as maize and beans required careful seasonal timing. In the Andes, climate can be harsh and unpredictable. In higher elevations, frost and drought are constant threats. Accurate knowledge of the solar year would have been essential for planting and harvesting at the right time. The later Inca civilization, which rose in the 15th century CE, is well known for solar worship. The Inca revered Inti, the sun god, and built structures aligned with solstices in their capital, like Cusco. However, Changkilo predates the Inca by more than 1,000 years. It shows that solar observation traditions in the Andes have deep roots. While the Inca used horizon markers known as sequays and pillars to track solar positions, Chanquillo stands as earlier evidence of similar thinking. It demonstrates that Andean societies independently developed systems for observing the sun's annual path. Excavations at Chanquillo reveal that the towers were carefully constructed from cut stone blocks and mud mortar. The builders understood the importance of sightlines. The observation points are positioned so that the entire row of towers fits neatly within the field of view. The alignment is not accidental. Modern researchers use computer simulations to reconstruct the ancient sky. By calculating the sun's position around 300 BCE and comparing it with the orientation of the towers, they confirm the accuracy of the alignment. The match is strong enough that most scholars agree Chanquillo functioned intentionally as a solar observatory. Unlike speculative astronomical claims made for some ancient sites, the evidence at Chanquillo is widely accepted within mainstream archaeology. The relationship between the towers and the solstices is measurable and repeatable. Yet Chanquillo was not just a scientific instrument, it was part of a social and ritual landscape. The presence of fortified walls suggests conflict or the need for defense. Ceremonial spaces indicate gatherings. Solar observation likely carried symbolic meaning as well as practical use. In Andean belief systems, mountains, rivers, and celestial bodies were often seen as living forces. The sun's return after the winter solstice may have been celebrated as renewal. Agricultural cycles were tied to ritual calendars that blended observation with spirituality. The Andes present unique environmental challenges. Elevation changes create microclimates. Coastal deserts depend on river irrigation. Highland communities face short growing seasons. In such conditions, precise seasonal awareness becomes a matter of survival. Chanquillo's 13 towers divide the horizon into 12 intervals between them. Some scholars have noted the symbolic similarity to 12 months of the year, though there is no direct evidence that the builders used a 12-month system identical to later calendars. What is clear is that the spacing allows consistent tracking of the sun's gradual movement. In 2021, UNESCO recognized the Chanquillo Archaeoastronomical Complex as a World Heritage Site. This designation reflects its importance as the earliest known solar observatory in the Americas. Beyond Chanquillo, other Andean sites also show solar alignments. At Machu Picchu, built by the Inca in the 15th century CE, the Intihuatana stone is positioned to mark solar events. At Cusco, pillars once stood along the horizon to mark the sun's rising points. Spanish chroniclers such as Bernabé Cobo described these pillars in the 17th century, though many were destroyed during colonial rule. While these later examples are well documented in historical texts, Chanquillo relies entirely on archaeology. There are no surviving written records from its builders. What remains are stones and shadows. The fact that such a complex observatory developed independently in South America shows that careful solar tracking is not limited to one region or culture. Across continents, ancient societies recognized that the sun's movement could be measured and predicted. The Andean solar observatories demonstrate a deep understanding of the relationship between horizon and sky. They reveal a tradition of observation rooted in the landscape itself. Rather than building towering pyramids, the builders of Chanquillo used a natural ridge as part of their design. When standing at the western observation point today, one can watch the sunrise move gradually along the towers over the course of the year. The experience is direct. No instruments are needed beyond the eye and memory. This simplicity is powerful. It shows how knowledge can be embedded in architecture and terrain. The sun becomes the moving hand of a giant clock, and the towers become its markers. Though Chanquillo dates to around 300 BCE, long after earlier calendar systems elsewhere, it stands as evidence of independent development. It reflects the universal human need to organize time according to nature's cycles. In the highlands and valleys of the Andes, agriculture demanded precision. Ritual life required regularity. Political authority may have been strengthened by control over seasonal knowledge. Through excavation reports, radiocarbon dating, and astronomical modeling, modern scholars have confirmed the function of these towers. They are not random ruins. They are deliberate markers of the solar year. As the sun rises over the Peruvian desert today, it still traces the same path it did more than 2,000 years ago. The towers of Chanquillo remain in place, silent but exact. They remind us that across oceans and mountains, ancient civilizations looked to the horizon and found a way to measure the turning of the year. In that shared human act of watching the sun, time itself became something that could be seen, understood, and built into stone. Chapter 10. The Julian Reform. Correcting ancient drift. For thousands of years, civilizations tried to measure the length of a year. They watched the sun rise at different points on the horizon. They marked solstices with stone. They tracked the flooding of rivers and the return of certain stars. Many arrived at the same number, 365 days. But that number, though close, was not exact. Over time, even a small error would grow. By the 1st century BCE, this slow drift had become a serious problem in Rome. The Roman calendar before Julius Caesar was complicated and unstable. It was based partly on lunar cycles and partly on political tradition. The standard year had 355 days. To correct the difference between the lunar year and the solar year, an extra month called Mercedonius was inserted from time to time. In theory, this kept the calendar aligned with the seasons. In practice, it did not. The decision to add the extra month was controlled by Roman priests known as the pontifices. These officials had political influence. By choosing when to insert or skip the extra month, they could lengthen or shorten a year. This affected terms of office, tax collection, and military service. Over decades, the calendar fell badly out of alignment with the actual solar year. By the time Julius Caesar rose to power, the Roman calendar was out of step with the seasons by several months. Spring festivals were drifting toward winter. Harvest events no longer matched agricultural reality. The disorder affected both religion and governance. Caesar understood that reform was necessary. During his time in Egypt, he had seen a more stable system in use. The Egyptian civil calendar had long been fixed at 365 days, divided into 12 months of 30 days, plus 5 extra days. Although it lacked leap years and slowly drifted, it was predictable and orderly. In Alexandria, one of the greatest centers of learning in the ancient world, Greek and Egyptian scholars studied astronomy with precision. There, Caesar consulted the astronomer Sosigenes of Alexandria. Sosigenes proposed a solution grounded in solar calculation. The true solar year is not exactly 365 days. It is about 365 and 1/4 days, or more precisely 365.25 days, as understood in antiquity. Sosigenes advised that the Roman calendar should be fixed at 365 days, with one additional day added every 4 years. This leap day would make up for the extra quarter day that accumulates annually. In 46 BCE, Caesar implemented the reform. That year became unusually long, lasting 445 days, to correct the accumulated drift. It was later known as the Year of Confusion. Extra days and months were inserted to realign the calendar with the seasons. Beginning in 45 BCE, the new Julian calendar took effect. The structure was simple and durable. The year was set at 365 days. Every 4th year included an additional day in February. This created an average year length of 365.25 days. The months were reorganized into the familiar 12-month pattern we recognize today. This reform removed the power of priests to manipulate intercalation. Leap years followed a fixed mathematical rule. Timekeeping became standardized across the Roman Republic, soon to become the Roman Empire. Historical records confirm the implementation of the Julian calendar. Roman inscriptions and official documents begin reflecting the new structure. Writers such as Suetonius and later historians describe Caesar's reform as a major administrative achievement. The influence of Egyptian knowledge was central. Although Egypt's earlier 365-day calendar lacked leap years, its solar basis inspired the Roman reform. Alexandrian astronomers, drawing on centuries of observation, provided the calculations needed for correction. The Julian system dramatically reduced seasonal drift. However, it was not perfect. The true solar year is slightly shorter than 365.25 days. It is approximately 365.2422 days. The difference is small, about 11 minutes per year, but over centuries it adds up. Still, compared to earlier systems, the Julian calendar was a major advance. It stabilized civic life. Agricultural planning aligned more closely with the seasons. Religious festivals occurred at consistent times of year. As the Roman Empire expanded, the Julian calendar spread across Europe, North Africa, and parts of the Near East. It became the dominant timekeeping system of the Western world. After Caesar's assassination, the Senate honored him by renaming the month Quintilis as July. Later, Emperor Augustus corrected a minor error in early leap year implementation and had Sextilis renamed August. In this way, the calendar carried political memory alongside astronomical calculation. For more than 1,600 years, the Julian calendar remained in use. It shaped medieval Europe and influenced Christian liturgical time. The calculation of Easter, tied to the spring equinox, depended on the calendar's structure. By the 16th century, however, the small inaccuracy in the Julian year had accumulated to about 10 days. The spring equinox, which had occurred around March 21st in earlier centuries, was falling earlier in March. This misalignment created problems for church calculations. In 1582, Pope Gregory XIII introduced a refinement known as the Gregorian Reform. Guided by astronomers such as Christopher Clavius, the new system adjusted the leap year rule. Century years would not be leap years unless divisible by 400. This change reduced the average year length to 365.2425 days, much closer to the true solar year. The Gregorian calendar did not replace the Julian structure entirely. It built upon it. The 12-month framework in the concept of leap years every 4 years remained intact, with minor adjustments. The modern calendar used in most of the world today is therefore a direct descendant of Caesar's reform. The line runs clearly from Egyptian solar observation through Alexandrian astronomy to Roman political authority and finally to the Gregorian refinement. When we look back at earlier civilizations, at Egypt's fixed 365-day system, at Mesopotamian intercalation, at Mesoamerican solar tracking, we see repeated attempts to match human timekeeping with the sun's path. Each culture solved the problem in its own way. The Julian reform represents a moment when accumulated knowledge was consolidated into a system strong enough to endure across continents and centuries. It turned experimental correction into permanent structure. Caesar did not invent the idea of a 365-day year. That idea was already ancient. What he did was apply consistent mathematical adjustment. He corrected inherited drift and anchored Roman time more firmly to the solar cycle. Today, when a leap day appears every 4 years on February 29, it reflects a decision made more than 2,000 years ago. It reflects the understanding that the Earth's orbit does not divide neatly into whole days. The story of the Julian reform is the final chapter in a long human effort to measure the year. From stone circles marking solstices to lunar intercalation in early cities, from Egyptian civil calendars to Roman legislation, the search for accuracy has been continuous. Timekeeping is not only about astronomy, it is about order, governance, ritual, and survival. It is about aligning human activity with cosmic motion. In 45 BCE, Rome chose to follow the sun more faithfully. That choice shaped the rhythm of Western civilization. And through later refinements, it shaped the calendar that guides daily life across the modern world. The drift that troubled ancient societies was not erased forever, but it was reduced to a whisper. And in that quiet correction, the ancient quest to measure the year found a form that still endures today.